Hey guys, welcome back. In working with HDFS lesson, we copied file to and from HDFS using copy from local and copy to local commands respectively. Copy from local does a write operation to HDFS because from the local file system we are writing a file into HDFS, whereas copy to local does a read operation because it reads a file from HDFS and write it to the local file system. We know that a file or data set is divided into chunks or blocks and stored across the nodes in the cluster. Imagine we are the client and we are trying to read a file from HDFS. And how do we know where the blocks are physically stored? We will answer those questions in this lesson. In addition to that, we will also see how the read and write operation works behind the scenes in HDFS. A Hadoop cluster has two types of nodes. The first type of node and the most important node in the Hadoop cluster is called the name node, also known as the master. The second type of node is known as the data node, also known as the slave. In HDFS architecture lesson under architecture chapter, we will talk in detail about the architecture of HDFS, where we will go in great detail about name node and data node. In this lesson, we'll look at the functionalities of the name node and data node on a very high level. Name node, also known as the master node, has the metadata of HDFS, meaning it has a list of files, the list of blocks that each file is made of, who created the files, when it got created, when it was modified, the permission of the files, etc. So it has all the information about HDFS and what is in HDFS. Hence, name node is a very important node in the cluster. Name node does not store the actual files or datasets. The files or data sets are stored in another type of nodes called the data nodes. Data nodes, also known as the slaves, stores the physical blocks for the files in HDFS. Usually there is only one active name node in the cluster, and you can have as many data nodes as you like in the cluster depending on the amount of data you would like to store in HDFS. So in short, if you take a file in HDFS, the data nodes will store the actual physical blocks for that file, whereas the name node knows the list of blocks that make up the file and the list of data nodes that stores the blocks for that file. And also information about the file, like who created it, when it was created, its permissions, etc. Let's say we want to read a file from HDFS, and the file is made up of 10 blocks. So we execute Hadoop fs-copy to local command from one of the data nodes in the cluster to copy the file from HDFS to the local file system. When we execute Hadoop fs-copy to local, a Java program is executed behind the scenes, which does a series of operations to read the file from HDFS. All these operations happen behind the scenes and it is transparent to us. We will now see step by step what happens behind the scenes. First, the client program trying to read the file will contact the name node to get the list of block locations for the file. If the replication factor for the file is 3, then for each block, the name node will return address of all 3 data nodes that stores a copy of the actual block. When the name node returns the list of data nodes that has a copy for each block, it also sorts the data node in terms of proximity to the client requesting the read. So the client can read the block from the closest data node. If you have 100 nodes in the cluster, how does the client know which node is the closest one? In a Hadoop cluster, the data nodes are physically organized into racks. The data nodes in a rack are connected to one another, and all the racks in the cluster are connected to one another. Let's say we have 2 racks, rack 1 and rack 2. And our client who is trying to read the file is running on rack 1 data node 2. There will be 3 replicas for a block, correct? Let's say the first replica is stored in rack 1 data node 2. The second replica is stored in rack 1 data node 6 and the third replica in rack 2 data node 5. Now rack 1 data node 2 is considered the closest data node to the client because the client is also running on the same node. The next closest node to the client will be the node which is on the same rack. In this case, it will be rack 1 data node 6. The next closest node to the client will be the node which is on a different rack. In this case, it will be rack 2 data node 5. If the client runs on a data node which does not hold a copy of the block, and if you have 2 data nodes on the same rack which holds the replica of the block, then one of the data nodes from the same rack will be chosen at random. So in essence, the closest node to the client is a node on the same rack as the client, and the next closest node is a node on a different rack. Okay, now going back to the read operation, the client will reach out to the data node which is closest and start reading the block. Once it is done reading block number 1, it will move on to block number 2 and then block number 3 and so on. Let's say our client is reading block number 3 and the data node it is trying to read from is not responding. The client will take a node of the data node which is not responding. So it will not try to reach the same data node again for the current read operation. And it will move on to the next data node that has the copy of the block from the list sent by the name node. So that even when a data node is down during the read operation continue to progress without any issues. That is it for the read operation. Now let's say you want to write a file to HDFS using Hadoop FS copy from local command. Let's see what happens behind the scenes when a client requests a write operation. The client will request the name node to allocate blocks for the file and the list of data nodes for each block where the replicas for each block needs to be stored. The name node will do few checks to make sure whether the user requesting the write operation has proper permission to do so and whether the file name already exists in the directory, etc. When all the checks are okay, it will proceed with the block allocation. The name node will now have to come up with a list of data nodes. While picking the data nodes to store the replica, the name node will pick the data nodes which are not busy and has enough space to hold the blocks. Now to pick the data nodes to store the replicas for each block, the name node will use a replica placement strategy. The default replica placement strategy will work like this. The first replica will be written on the same node as the client requesting the write. The second replica will be placed on a random data node on a different rack from the first one. The third replica will be placed on a data node which is chosen at random on the same rack as the second one. Now when the nodes are selected, a data pipeline is formed and the data for the block will be written in the form of packets. The first node will then store the packet and pass it on to the second node. And once the packet is stored on the second node, it will be passed on to the third node. Once all three nodes stored the packet, an acknowledgement will be sent back indicating a successful write of that packet. Once all the packets for the blocks are written, the write operation will move on to the next block. Let's say the block we are writing is named block 123. While writing block 123 on node 2, node 2 suddenly went down in the middle of the write operation. Now, how do we handle this failure? Let's look at how HDFS handle failures during write operation. First, the packets for block 123 are moved to the front so that node 3 will not miss those packets. Next, the block name will be changed. Why? If we keep the block name as block 123, when node 2 finally recovers, it will claim that it has block 123. But the block 123 is not complete since node 2 went down in the middle of the write operation. Let's say block name will be changed to block 456. Now when node 2 recovers and claims that it has block 123, name node will know that block 123 is non-existent and will order node 2 to remove block 123. dfs.namenode.replication.min indicates the minimum number of replications that is needed for a block. By default, it is 1. In case of such failure, the write operation will succeed as long as the block is returned to at least one node. Later, the name node will coordinate with the data nodes and arrange to write the missing replicas. That is how the write operation works. So in this lesson, we saw how the read and write operation works behind the scenes. In the next lesson, we will perform a read and write operation against HDFS by writing a Java program. With that, let's wrap this lesson. See you in the next lesson.